Welcome to solverfy.
This is the answer to Chapter 15, problem number 69 from the Smith Organic Chemistry textbook. And this problem asks us about resveratrol. And we're asked to draw all resonance structures for the radical that results from homolysis of the OH bond that's drawn in red in the textbook. And we're also asked to explain why homolysis of that OH bond is preferable to homolysis of the other two OH bonds. And so I've drawn the basic structure of this molecule out 9 times here. There are 9 resonance structures that we're going to need to draw. And so in order to try to save some time, I've drawn the base structures out, and then we can go ahead and take a look at the resonance structures. Whoa. Okay, and so the first one is going to be here. So the OH bond has been cleaved homolytically. So there's going to be a radical, an unpaired electron on that oxygen. And the rest of the molecule is going to be exactly as it appears in the starting material. Okay, so our next resonance structure we can draw by moving the radical electron and a double bond. So we can have double bond here, and we can have our double bonds here and here, and that is going to put the radical on this carbon. And in order to do that, we could draw it like this. So one of the electrons from here and this electron come together to make the new bond, and the other electron from that double bond goes there. Okay, so then we have a next resonance structure that looks like this. Oh, and I suppose I should draw the H's. So I left H's off of these O's because eventually we're going to be seeing the radical there as well. Okay, so our next resonance structure still has the double bond here, and then we have a double bond here and here, and now our free radical is on this carbon. And to get to here, it would look like this. So one electron from there, the free radical come together to make the new bond, and the other electron goes there. Okay, so from this third structure here, we can go one of 2 ways. So just thinking about finishing moving the double bonds around this first ring, we can draw structures that will look like this. So now our lone pair is, or pardon me, our unpaired electron is here. And again, we can get there like this, just to show the movement of electrons. Okay, and then our last potential resonance structure without leaving this first ring is going to look like this. And so we have the unpaired electron back on the oxygen now, like how we started. However, what's different is the double bonds have all moved around the ring. So if you compare this resonance structure to the first structure, the double bonds are all in different positions. Okay, and so to get there, we would do this. So one of those electrons and that electron come together, and then the other electron goes to the oxygen. Okay, so the 4 resonance structures along the bottom of the screen, let me go ahead and erase some of this. Then fill that back in. Okay, so from here, where we had our unpaired electron there, we sort of said that would go up, but it could instead go to the left. So it could go like this. It could form a new bond here with one of these electrons, and the other electron could go to that carbon. And so if that's the case, we're going to have our double bond be there, or pardon me, our unpaired electron be there. And so we'll have this. And now we have a double bond right here. Okay, and so from here, we can continue moving around this other ring, or towards this other ring, I guess. So if the electrons move like that, we'll get a structure that looks like this. Now we have double bonds here and here. Unpaired electron here. Okay. And so from there, we can just continue to move this around the ring. So like this. Will put us here. And I guess I could have drawn these H's in because it looks like we're not actually going to delocalize this onto these H's. I thought at first glance that we would, but now I'm seeing that that's not going to be possible. So like this and like this. And our double bonds are now here and here. And our unpaired electron is right here. And then lastly, we can move it one more time by doing this. And so that will give us this structure with the unpaired electron right here. Okay, and so that's the 9 resonance structures that we can draw here. And yeah, as you can see, this ability to delocalize across both rings is what makes for the large number of resonance structures. And it's because of this that this oxygen-hydrogen bond is preferentially cleaved. If we were to cleave one of the other OH bonds, we would not be able to delocalize across both of the rings. Yeah, and so breaking one of the other ones would only allow us to delocalize over this first ring, and so that's not going to be as preferable. We wouldn't be able to draw as many resonance structures, and since there aren't as many resonance structures, we can say that radical is less stable, and the more stable radical is always going to be the one that forms. And so that's why this oxygen-hydrogen bond is preferentially cleaved. And that's the answer to chapter 15, problem number 69.